Hello, statistics students. Today we're going to learn how to do hypothesis tests for proportions. In our last chapter, when we did confidence intervals, here was the order we went in. If we were estimating mu and knew sigma, we used a z-table. If we were estimating mu and didn't know sigma, we used the t-table. And if we were estimating a population proportion, we went back to the z-table. Well, now in hypothesis tests, if we're doing a hypothesis test for mu and we knew sigma, we're going to use a z-score. If we're doing a hypothesis test about mu and we don't know sigma, we're going to use a t-score. And just as we did above, when we're dealing with proportions, we're back to z. So the only thing that changes in our steps for doing a hypothesis test from means to proportions, all of this remains the same, assuming we're using the critical value method, the rejection region method. The only thing that changes is how we calculate a z-score. And it's p hat minus p0 over this standard error. I'll show you in a minute why these are I'll show you why, or remind you, gee whiz, that p hat, the only place you encounter p hat in this formula is here. All the rest of these are p0 and q0 because your null hypothesis says that p is equal to p0, which means your curve has to be centered at p0 so that you find how far away your sample is from p0. And if the curve's centered at p0, then it has a standard error of square root of p0 q0 over n. Then we finish our hypothesis test. One crucial point that we haven't had to deal with before, your sample size can be no bigger than 1/10 of your population size. If your sample size is too big, then the proportion, your sampling distribution of your sample proportions is not normally distributed anymore. So we have an upper limit to our sample size. What's the lower limit for our sample size? Give you a hint. How big does a sample have to be in proportions so that we can start saying that the sampling distribution is normally distributed? All right, if you can't answer that, be sure to ask about it in class. So now for proportions, we have a lower limit for our sample size, and we have an upper limit of our sample size. And that upper limit is 1/10 of the population. As I explained earlier, if the curve is, if your sampling distribution is centered at p0, which this central limit theorem says it will be, then we want to find how far our sample is from p0. And if the curve is centered at p0, it's the p0 q0 over n that's going to be the variance of that sampling distribution. And you take the square root for the standard dev of that sampling distribution. Now down here, when we were doing confidence intervals in our last chapter, everything was hat. And that was because we didn't have any other numbers. But in the hypothesis test, we do. We have p0 as well as p hat. So let's do an example problem. What's the probability that candidate A is going to win? In other words, candidate A gets more than 50% of the vote. So the alternate, what I'm trying to prove candidate A is going to win. So my alternate is P is greater than 1/2. That's obviously a right-tailed test. And the complement of that is P is less than or equal to 1/2. That's my null. So 1/2 is my p0 value. And we're just going to let alpha be 5%. So I'm going to survey 1,000 randomly selected voters, and I get candidate A had 525 yeses out of those 1,000. Candidate B had 475. Is that enough, given sampling variation, to conclude that candidate A is over 50% or not? So my p hat is 52.5%. It's 525 out of 1,000. But the curve is going to be centered at 0.5. So 1/2 times 1/2 over 1,000 takes the square root, gives us 0.016. So if I go over one standard dev, where I've eyeballed it here to the inflection point, one standard dev, you add 0.016 to 0.5 and you get 0.516. But we got, let's see, our z-score is, well, actually what we got for a p hat was 0.525, which is right here. And that's 0.516. Z-score, okay. So our 0.525 converts to a z-score of 1.581. You can see that I've substituted the numbers in appropriately. You do not put 525 out of 1,000 and 475 out of 1,000. These are P0 and Q0. So I did the rejection region method on this one. In my rejection region, if I wanted a 5% upper tail or 5% right tail, that's a Z critical value of 1.645. Remember, 1.645 marks off the middle 90%, which gives you a 5% tail up here and a 5% tail down here. We aren't interested in this tail, but we know that that 5% upper tail is at 1.645 standard devs. Well, we're only at 1.581 standard devs. So we fail to reject the null because we are not in the rejection region. We fail to reject the null at the 5% level. There is not enough evidence to conclude that candidate A has over 50%. Now you say, but candidate A had 52.5%. That was in a sample. And what we see here is that if you were to continue taking samples of size 1,000, it would not be uncommon to get a sample of 525 out of 1,000 or greater. So to make sure that there's less than a 5% chance that that happens, we haven't set an alpha of 5%. In our rejection region, we would have to get a sample out here before we could conclude that candidate A has over 50% support. We didn't get that sample. So there's not enough evidence. Does that mean that we've proven that candidate A's support is less than 50%? I don't know how we could prove that when our sample was 525 out of 1,000. It's just that we failed to reject it. So we're going to conclude that this is true pending further evidence. But we certainly didn't prove this is true. In fact, our little evidence we have suggests that candidate A has over 50%. We just don't have strong enough evidence to, at the 5% level, to conclude, yeah, candidate A is definitely over 50%. So while we didn't prove the null is true, we didn't get enough evidence to reject it. So here's the three components of my conclusion statement. So as you can see, doing a hypothesis test, except for calculating the Z statistic, is just like doing the hypothesis tests for means. We're using the same process, the same step-by-step procedure, and we're using the same criteria for whether we reject or fail to reject the null hypothesis. So that's all we have for now. Have a great day.